Alright, so we are trying to discuss the notion of focusing attention at a point, which means you are trying to understand geometrically how to study functions at a point, and the device for that is commutative algebraically the device is called the local ring. So I told you last time that if x is a variety, of course, which means that x could be either an affine variety or a quasi-affine variety or a projective variety or a quasi-projective variety, and you have P, a capital P, a point of x, we have the local ring of x at P. So well, in fact, to expand it, it's actually called the local ring of germs of regular functions of x, the local ring of germs of regular functions at P. Okay, so so in fact, let me write this as local ring of germs of regular functions at P. And how was this defined? This was defined in the following way. We took OX P tilde to be the set of all pairs of the form U comma F, such that U contains P, U is an open subset of X, and F is a regular function on U. So you take the set of all such pairs, and then what you do is you go modulo an equivalence relation, okay, to get a surjection from this into the local ring. And what is this equivalence relation? The equivalence relation is, well, UF is equivalent to VG if and only if by definition F restricted to U intersection V is equal to G restricted to U intersection. Okay. So so this is an equivalence relation. You are just identifying functions on the intersection, and of course, for this this is also equivalent to just assume requiring that F restricted to W is equal to G restricted to W for an open W inside U intersection V, because if a regular function if two regular functions coincide on an open non-empty open subset, then they of course coincide everywhere, right. So I need not require that the point P is in W. So this is a local ring, and if you start with an element here u comma f, its image here is written with a square bracket and it is called the germ of the function f, okay. And the germ of the function f, whenever a pair u comma f is equivalent to a pair v comma g, then in the local ring they will give rise to the same germ, okay. The germ of f and the germ of g will be one and the same, right. So, and I told you that OXP is a local ring, is a local ring with unique maximal ideal MXP, and MXP, what is the maximal ideal? It is germs of all those functions which vanish at the point P. So MXP is all those germs u comma f such that f of p is 0. So germs of those regular functions defined in a neighborhood of the point P which vanish at P, okay. And so we saw that how did we show that this is a maximal ideal here? We showed this is a maximal ideal here by showing that if there is a germ of which does not vanish at P, then it will by continuity not vanish in an open neighborhood containing P, and on that open neighborhood it will become invertible, okay. So so it will become a unit. So in other words, a germ of a function that does not vanish at P, namely an element here which is outside here, is a unit. So you have a characterization of local rings in commutative algebra, which is a simple lemma. You can prove it for yourself. If you have a commutative ring with 1 and if there is an ideal such that everything outside that ideal is a unit, then that ideal has to be the maximal ideal, unique maximal ideal, and therefore the ring will become a local ring, okay. So this is what is happening here. So you have a commutative ring with 1 and you have this is obviously an ideal and everything outside it is a unit, so this is the unique maximal ideal for this local ring, and this ring is local, okay. Of course all these are even K algebras, okay. OXP is actually a K algebra. So so the point is so focusing attention at a point corresponds geometrically focusing attention at a point, which means trying to study regular functions at a point, that commutative algebraically boils down to studying local rings, okay. Now the point I want to make is that why is this important? So here is the lemma. So the lemma is by the way, I forgot to tell you that there is an obvious way in which addition and multiplication is defined here, okay. Maybe I will just recall it. You have u comma f, you have a germ, you add it with v comma g by simply adding the functions on the intersection. So you just take u intersection v and take f restricted to u intersection v plus g restricted to u intersection v, okay. So you take the germ of this pair. I asked you to check that this addition which is defined like this using representatives of equivalence classes is well defined, it is pretty easy to see. So of course instead of addition I could also put multiplication, and if it is multiplication I will have to put multiplication here, of course. And the 0 element is given by the function 0, the germ of the function 0, and the unit element the multiplicative identity element is given by the constant function 1, which is also, of course constant functions are all regular functions, okay. So 0 and 1 are just given by the germ of the 0 function, the constant function 0, and 1 is just the germ of the constant function 1, which takes the value 1, okay. So now the lemma is the following: if U is an open subset of X containing P, then OXP is the same as OUP, okay. So so this is the important, this is the localness, namely the local ring at a point of a variety depends only on depends only on the neighborhood of the point, okay. It does not depend on the ambient variety. So if you take so if you have a point, if the point P of your variety is lying in an open set, okay, then of course U is an open subset of a variety, and therefore U, and of course U contains a point P, so it is non-empty, alright, and it is of course irreducible, okay. And the point is that an open subset of a variety is also a variety, okay, an open subset of a variety is also a variety, right. Whether your so this is a fact that you can check using simple topology. An open subset of a variety is automatically a variety, right. So of course if the variety is an affine variety, an open subset will become a quasi-affine variety. If the variety is a projective variety, the open subset will become a quasi-projective variety. If the variety is a quasi-affine variety, then an open subset of that will continue to be a quasi-affine variety. If it is a quasi-projective variety, an open subset will continue to be a quasi-projective variety, okay. So in any case an open subset of a variety is again a variety, right. Therefore I can think of the local ring of the point P with respect to the variety U, okay, and there is no difference between the local ring of the variety, local ring at P, whether you are considering P as a point of U or P as a point of X, okay. That is the purpose of the lemma. So well, what is the importance of this lemma? The importance of this lemma is the following: give me any variety, you know, we proved last time that any variety can be covered by finitely many open subsets, each of which is isomorphic to an affine variety. Therefore if you give me any variety and give me a point on a variety, okay, I can choose an affine open subset, I can choose an open subset containing the point which is isomorphic to an affine variety, and therefore by this lemma I just have to calculate always the local ring of an affine variety at a point, okay. That will give me the local rings of any variety at any point, okay. And when you calculate the local ring of an affine variety at a point, there is an explicit formula for that in commutative algebra. It is simply given by the localization of the affine coordinate ring at the maximal ideal corresponding to that point, okay. That is what I will show next, okay. So this lemma is very useful, namely it tells you what the local ring looks like, at least more explicitly in terms of commutative algebra. This definition of local ring here is a very general process. You could do it in very general circumstances. You could take X to be a topological space, and for functions you could just take continuous real valued functions or continuous complex valued functions, or you could take X to be manifold, say a domain in Euclidean space, and you can take functions to be, you know, so many times differentiable or infinitely differentiable, namely C infinity functions, or you could even take X to be a domain in the complex n dimensional space, and you could take the functions to be holomorphic functions, holomorphic in each variable, and you can always do this process, and this process will always lead you to a local ring, okay. So the process is very general. So the fact that you are getting a local ring is very beautiful. It is something that tells you that local rings come out of geometry by focusing attention at a point. But then the question is, what is this local ring? If you ask the question what this local ring is, can you write it down? as some nice ring that you know in terms of rings that you know, then the answer to that comes from this lemma. For example, if you choose U to be an affine open subset of X, that is an open subset of X which is isomorphic to an affine variety, then what I am going to say later on will tell you how to write down that local ring. Okay, alright. So you see, so let us prove this. Is very easy to prove, it is pretty easy to prove. So the proof is rather simple. So you know you have OXP so you have OX or rather I should say I have OXP tilde, okay, and there is OUP tilde, okay, and the quotient of OXP tilde by the equivalence relation as I have defined here is going to give me the local ring OXP, and similarly if I take the quotient by this equivalence relation here I am going to get the local ring OUP, okay. And what I want to say is to say that these two are isomorphic, it is very simple. So what I do is I give a map from here to here, okay. So namely you give me U comma F, here you give me an element here, so this consists of a pair, which has a function f which is regular on the open set U which contains the point P. Maybe I should not use the same U, let me use something else, let me use V because U is already fixed, let me use V. So if you have a pair V comma F, then I have V an open subset of the point P, F is a regular function on V, okay. Now after all I can simply send it to, I can just restrict it to V intersection U, so I can just take V intersection U comma F restricted to V intersection U, I can do this. See, a restriction of a regular function to an open set continues to be a regular function because the notion of a regular function is local, okay, that is one thing. Then the second thing is any two open sets, any two non-empty open sets will always intersect because of irreducibility, okay. So all our varieties are irreducible, so any two non-empty open sets will intersect, any non-empty open set will be irreducible, it will be dense, okay. That is the coarseness of the Zariski topology, right. So there will always be an intersection, and of course the intersection will contain the point P because P is already in U, P is also in V, so P is also in U, V intersection U, and so this is a well defined map like this, alright. And what you must understand is that this map will also respect the equivalence, namely if two functions on X, if two regular functions in neighborhood of the point P coincide in a smaller neighborhood, they will also do so when you restrict them to these functions to U, the intersection with U, okay. So what this will tell you is that this will induce a map like this, so that this diagram commutes, okay, you will get a map like this, okay. And it is easy to check that this map is actually an isomorphism, okay. In fact you can check that this map is it's a natural identification, okay. So what you do is the fact that you need a map like this boils down to checking that this map respects the equivalence relation, okay. So which means that if two things are equivalent here, then the images there are equivalent. Once you have that, this map goes down to a map like this, okay. And then which means that this map is not just a map of sets, but it is also a map which preserves the equivalence relation on these two sets, okay. So it goes down to a map of the equivalence classes, okay. So you have a map like this, and then what I want to say is that this map is you can explicitly check that this map is both injective and surjective, because you know, see, if I have a germ of a function V comma F, well the map that is going to be here is going to be, I am going to send V comma F to VU intersection V comma F restricted to U intersection V and germ, okay. This is going to be the map here, alright, and because this map is induced by this map, alright. Now you see, now it's very easy. Why is this? It's very clear that this is going to preserve both the addition, and this map is going to preserve your addition, multiplication and so on. So this will be a K algebra homomorphism. It's going to preserve addition, multiplication. It's going to take 0 to 0, 0 element to 0 element, okay, and it's going to take 1 to 1, okay. So this map is you can almost see that, you know, the germ of f at the point P where f lives on V is going to be literally the same as the germ of f restricted to U intersection V, because after all it is the same function, you have just restricted it and it should define literally the same germ. So in fact this should be thought of as actually an identification, but if you want to formally say it, you have to say it's a K algebra, it's a homomorphism, it's injective and surjective. So the fact is, why is it injective? If this is 0, okay, if this germ is 0, it means that the function f restricted to U intersection V is equal to the 0 function on a smaller open subset of U intersection V, which contains the point P. But then but if two regular functions equal on an open set, then they are equal everywhere. So it will tell you that f itself is identically the 0 function on V, okay. So the moral of the story is that if something goes to 0, then this is 0, that tells you that this is injective, okay. And then how will you get surjectivity? If you give me anything here, actually the beautiful thing is anything here is also an element here. So actually there is a map in this direction also, namely you give me any if you give me any function defined on an open neighborhood inside U, if you give me a regular function on an open neighborhood inside U of P, that's also an element here, okay. So there is a reverse map, okay, and that will introduce a reverse map here, alright. So that is the reason why it's surjective. So the fact is that OXP to OUP is an isomorphism. This is an isomorphism. So it's, so you know, so it's obviously an isomorphism, but you know, we tend to treat it as an equality. We tend to treat it as an equality with the understanding that you are literally taking the germ of the same function but restricted to a smaller neighborhood, okay. So so that's the proof of this lemma, okay. Now so what is a corollary to this? Very important corollary to this is if x is a variety and P belongs to X, choosing U to be an open subset of X isomorphic to an affine variety containing P, we see that all possible local rings are can be computed up to K algebra isomorphism as local rings of points of affine varieties. So this uses the important fact that I stated in the previous lecture that any variety affords a finite open cover, a cover by finitely many open sets, each of which is isomorphic to an affine variety. Okay, it uses that fact. So so finally so there's another thing that has gone into in between the lines, which I should have said, but I'll say that now. So I want to say the following thing. I want to say that this local ring, this is an invariant, it is an invariant of the point on the variety. Okay, so so what I'm trying to say is that it doesn't change under isomorphisms. So you know, if you have a variety and you have a point, then you have the local ring at that point. If this variety is isomorphic to another variety, okay, and under this isomorphism this point goes to another point, then this isomorphism will automatically induce an isomorphism of the local ring of the source variety at the source point with the local ring of the target variety at the target point. Okay, so you will get it automatically because the isomorphism will be induced by the pullback of functions. Okay, so let me write that. Maybe I should say that, maybe I should have said that before this. So let me say that the local ring of x at P is an invariant. So what's an invariant? An invariant is something, an invariant of a certain object, geometric object, or an invariant of a mathematical object is something that doesn't change or changes only up to isomorphism if you change the object up to an isomorphism. Okay, so what I am trying to say is that, you know, if you change x and p up to isomorphism, then the local ring will change only up to an isomorphism. Okay, so that is, if phi from x to y is an isomorphism of varieties, then we get an isomorphism phi of k algebras of O y phi p with O x p. Okay, so you know, the situation is that you are having you have x comma p, this is called a pointed variety, that's a variety with a point. Okay, and you have this map phi, which is an isomorphism that carries x comma p to y comma phi p. Okay, so when I write a pair like this, it's a variety and a point on it. Okay, and the map is just not supposed to respect the variety, I mean it's not supposed to just go to this variety to that variety, but it's also supposed to take this point to that point, which is what it does. And the point is that the local ring of x at p will be isomorphic to the local ring of y at phi p because of this isomorphism. And the answer is, the reason is very simple. See, because you see what's going to happen is you have x, you have y, okay, and you have phi. So this phi will induce by pullback of regular functions. So you know, phi is a morphism of varieties. Basically phi is of course an isomorphism, but if phi is just even a morphism of varieties, it's supposed to pull back regular functions to regular functions. Okay, so phi is going to induce a pullback, so the pullback is going to be phi upper star, and what it's going to do is that, you know, it's going to go in this direction. You give me a regular function on an open subset y of v, okay, then I'm going to get a regular function on the open subset phi inverse of v of x. Okay, so if you have y and v an open subset of y, then phi inverse v is going to be an open subset of x, okay, and phi will restrict to phi inverse V and take it into V, this phi restricted to phi inverse V will be a morphism of the variety phi inverse V into V, okay, and give me any regular function on V. By composing it with phi I will get a regular function on phi inverse V, that is the pullback map. So this map is just, if you give me a G here, I am going to get the pullback, which is just G followed by first apply phi then apply G, this is phi, this is the pullback, okay. This is part of the definition of a morphism. The definition of a morphism is a continuous map which pulls back given any target, given any open subset of a target and given a regular function on it, namely given a regular function on an open subset of the target, then it pulls it back to give you a regular function of the inverse image of that open set on the source, okay. So this is what happens, and you can see that once you have this, then you have Oy phi p tilde whose quotient by the equivalence relation as I defined earlier is going to give you the local ring Oy phi p, and you have Ox p tilde, this is whose quotient by the corresponding equivalence relation is going to give you the local ring of x at p, okay. And the fact is that there is a map like this, this is induced by phi upper star, okay. Namely what it does is, if you give me a V comma G, it will send it to phi inverse V comma G circle phi, okay. It is going to send a pair here to a pair here, okay, and what is going to happen is that this is going to of course respect the equivalence relations, okay, and therefore you are going to get a map like this, okay. So this is via phi star, okay, and this also via phi star, okay. So what this diagram shows is that the moment you have morphism of varieties, then and you take a point P, if it goes to a point phi p, then you immediately have a K algebra homomorphism of local rings in the opposite direction, okay. So this is a K algebra homomorphism. This diagram of course commutes, so does this, okay. So you must think of this as an infinitesimal version of the following fact. See, whenever you had morphism from one affine variety to another affine variety, it induced a pullback from the regular functions on the target to the regular functions on the source, okay. When you have a morphism from one affine variety to another affine variety, it induced a pullback of regular functions from the regular functions on the target to the regular functions on the source. If you take the infinitesimal version, what the infinitesimal version is going to be this, it is going to pull back germs of regular functions on the target at a point to germs of regular functions of the at the source at the point of the source which corresponds to the target point, okay. So it is very simple, you have a regular function on V, you compose it with phi, you get a regular function on phi inverse V. So the germ of a regular function on V at phi p is going to, after composition with p, is going to give you eventually is going to define the germ of a regular function at p itself, okay. So a regular function in a neighborhood of phi p is, after composition with phi, is going to give you a regular function at p, okay, a regular function in a neighborhood of p, and therefore you are going to get a map on germs, you are going to get this. But the point is that if phi is an isomorphism, okay, then you also have a map in the other direction, and you can check that these two maps are inverses of each other, okay. So whatever I have written here for phi, I can also write for phi inverse, because I can do that if I know phi is an isomorphism. So whatever I wrote here, I can write everything for phi inverse, so I will get a map like this, okay, and then you can check that these two maps are inverses of each other, okay. These two maps are inverses of each other, and therefore these two, that will give you an isomorphism of this with this, okay. So phi star, so you know this map via phi by phi star, I'll call this as phi star, this is phi star going down to the point phi p, so I'll call this via phi star, okay. Let me not complicate the notation. So phi star and phi inverse star, which is from O xp to O y, so phi inverse is going to be in this direction, so it is going to be from OXP to OY phi p, okay, are inverses to each other and hence we get that phi star is an isomorphism of K algebras, okay. So this is the fact that, I mean, this is what this remark says, that you know the local ring is an invariant. If you change the variety up to isomorphism, the local ring will not change, it will change only up to K algebra isomorphism, okay. And of course we do not distinguish between, we try not to distinguish between our varieties that are isomorphic in the geometric sense, and we do not try to distinguish between K algebras which are isomorphic in the commutative algebraic sense, okay. So well, alright, so this is what I am trying to say here. If x is a variety and p is a point of x, and you choose u to be an open subset of x which is isomorphic to an affine variety, then under that isomorphism the local ring of x at p, which is the same as the local ring of u at p according to this lemma, will be isomorphic to the local ring of that affine variety to which u is isomorphic at the point which the isomorphism carries p2, okay. So so somehow this has to be thought of before one can understand that properly. Now I come to the, so the big deal is how do you calculate what is the formula commutative algebraically for the local ring of of an affine variety at a point, okay. So this is the, here is the theorem if x is an affine variety and p in x is a point, corresponding to, okay, so let me make a small then OXP is canonically isomorphic as K algebras to AX localized at MP as K algebras. So this is isomorphic as K algebras, where MP is the maximal ideal of AX which is the same as OX corresponding to P. Okay. So here is the formula for the local ring at a point of an affine variety. So the local ring is just gotten by taking the affine coordinate ring of the affine variety, which you know is also the same as the ring of regular functions, okay. These two are the same for an affine variety, and then you localize at the maximal ideal that corresponds to this point, okay. So of course localizing at an ideal means that you should for this to make sense you have to localize at either certainly at a prime ideal, because localizing at a prime ideal or a maximal ideal means you invert everything outside, all the elements outside the prime ideal or the maximal ideal. So this means take the ring Ax and invert all the elements which are not in the maximal ideal corresponding to the point P, okay. Then the other thing is, of course, so now I want you to recall that, you know, according to the Nullstellensatz, okay, the points of X, the points of the affine variety X are in one-to-one correspondence with the maximal ideals in Ax, okay, and this is just because of you know, the Nullstellensatz that's more general, that can be more generally applied to the affine space in which X is embedded in, okay. So so here is a proof of the theorem, which is also pretty easy. The proof is, well, so you have Ox, which is Ax, okay, and from Ox you have the following map into OXP. So here is my map. You give me any regular function f, you just send it to the pair x comma f and the germ of that. So simply send every regular function to its germ, okay. So f is in Ax means that f is a regular function on all of x. Ax is the same as Ox, okay. So the whenever you write a pair u comma phi has to be a regular function on u, okay. So here f is a regular function on x, so it makes sense to write the pair x comma f, and then I am taking the germ, that is why I put the square bracket, okay. This is of course a K algebra homomorphism, this is K algebra homomorphism, that is easy to check, and well, you can also see that it is injective, because you see you know, if the germ of f at the point P is 0, it means that f coincides with this 0 function in a neighbourhood of P, but then it has to coincide with 0 on all of x, okay. So if this is 0 then this is 0, so this is an injective homomorphism, okay. Then you also have the localization map, so you have the localization map, this is the localization of this ring Ax at the maximal ideal corresponding to the point P, okay. So of course, you know, MP is all those functions in Ax which vanish at P, that is all, okay. It is a maximal ideal, right. And so you know, the fact is that you get a map alpha like this with, because of the universal property of localization, okay. See, if you start with G in Ox such that G of P is not 0, okay. Suppose you start with a regular function, global regular function on X, G, an element of Ox which is the same as Ax, and suppose G is not going to vanish at the point P, then this is equivalent to saying that G does not belong to MP. So this implies that you know, G does not belong to MP, and if G does not belong to MP, its image in the localization will become a unit, because the localization has this property that it inverts all the elements which are outside MP, and since G is not in MP, it is going to be inverted. So G under this localization map goes to a unit in MP, okay. And so you have this fact, alright, and you should see that G will also go to unit there. If I take the image of G in Ox, here also it will go to a unit. Why? Because you see, G will go to the germ of x comma G, okay, but the germ of x comma G will not belong to MXP, which is because MXP is supposed to be the germs of all those regular functions which vanish at P. So but G does not vanish at P, therefore the germ of G in the local ring corresponds to an invertible element, a unit. So you see, every element which is outside the maximal ideal MP is going to a unit here, and therefore this there is a universal property of localization which says that whenever you have a ring homomorphism from a given ring to another ring with the property that it inverts all the elements that are inverted by the localization process, then that homomorphism has to factor from the localization. The localized ring is in some sense the initial object, okay. So this is called the universal property of localization. So there exists alpha, there exists a unique alpha by universal property of localization, and you know it's very easy to write down what that alpha is. See alpha, see an element here will look like f by g, okay. An element in the localization will look like f by g, where f is a regular function, g is a regular function, but g is not in MP, that means g does not vanish at p. That is how elements here will look like, okay. And alpha of f by g is going to be very simple, it is going to be just you just take the image under this, so you get the germ of f times, you see the germ of g is invertible, so it will be this times germ of g inverse, okay. This is what it will be. And what is this? This is, you know, if you think about it, this is just, you know, this is just xf germ of f times germ of g inverse is what? I mean g does not vanish at the point p, so g will not vanish in a neighbourhood of the point p, which means that dg, the set of all points where g does not vanish inside x, so dg will contain p and it will be an open set which contains p, okay. And you can write 1 by g as a regular function on dg, so this will be just x intersection dg comma 1 by g, this makes sense, this is what it is. And so you know so this is how the map is defined, this is how the map is defined. So in fact if you take the product, you have to take the product on the intersection, so it will be just x intersection dg f by g, this is the map, because you see f by g is certainly a regular function on x intersection dg and it is a germ of this function, so this is the map, okay. Now you can see very easily that this map is both injective and surjective, okay. Why is it injective? Well, you know, if f by g vanishes, okay, if the regular function f by g vanishes in a neighbourhood of the point, then you know, see what it's going to tell you is that it's going to tell you that yeah, so what will happen is that it will tell you that f by g and 0 and the 0 function, they are equal on this open set x intersection dg, which is an you know, dense open subset of x, okay. So that will tell you that f has to be 0, okay. So so the moral of the story is that you will easily see that this is both this is injective, and why it is surjective is because, well, you start with the germ of a regular function at the point p, okay, then in a neighbourhood of the point p it is going to look like f by g, and it is going to be the image of under this the same f by g under alpha. So it is trivially surjective, it is trivially surjective just by the definition of a regular function regularity at a point, okay. What is an element here? An element here is germ of a regular function at the point, okay. But what is a regular function at a point? It is supposed to be given by, it is a regular function is something that has to locally look like a quotient of polynomials. So a regular function at this point is in a neighbourhood of that point is going to look like f by g, okay, where f and g are regular functions, where f and g are regular functions, f and g are polynomials in fact, okay, polynomial functions on the affine space in which x is embedded, okay. So but then f by, so that but then that f by g will also be here, it makes sense of an as an element here, and alpha will carry it onto your germ, so it's surjective, it's injective, it's surjective, so it's an isomorphism. So clearly alpha is an isomorphism. So it's just a moment's thought will tell you that alpha is an isomorphism. So in other words, you have this formula, okay. So the moral of the story is that whenever you want to calculate, whenever you want to go down to commutative algebra and try to focus attention at a point, all you will be doing is always trying to look at this ring, which is, you know, you will have some finitely generated K algebra which is an integral domain. These are how affine coordinate rings of varieties look like, and then you will have to localize it at a maximal ideal, okay. And so these are the rings that you have to study in commutative algebra if you want to get what happens geometrically at a point on a variety. So the study of the geometrically the study of functions in a neighbourhood of a point on a variety, that is reduced to the commutative algebra of trying to study localizations of finitely generated K algebras which are integral domains, such rings which are affine coordinate rings at maximal ideals, okay. So this is what one has to do, okay. So this is how local rings enter into geometry, okay. And but interestingly enough, the local rings were produced by geometry, okay. They were defined by geometry, and then here is how they come commutative algebraically, okay, at least in the case of algebraic geometry. So I will stop here.